Good day, everyone. My name is Kato Bilid of BS ECE 3A. Today I'm going to present to you my performance task number 3 in ECE 23. The discussion for this performance task will cover pulse modulation, pulse width modulation techniques, and the sampling method used in PWM. Mainly, we are going to focus on PWM and NADD. Now, what is pulse modulation? Pulse modulation is a type of modulation wherein the carrier is usually a series of regularly recurrent pulses, or it is a type of modulation in which the signal is transmitted in the form of pulses. It can be used to transmit analog information. So modulation results in sampling the baseband signal at regular intervals and converging the sampled results into PAM, PWM, or PPM. So from the previously learned lessons, we have types of pulse modulation. We have analog and digital. So under analog pulse modulation, we have pulse amplitude modulation, pulse width modulation, and pulse position modulation. Under digital pulse modulation, we have pulse code modulation and adaptive delta modulation. Modulation schemes. The modulation schemes truly at the heart of the Class D amplifier refers to the technique by which the audio signal is encoded as a modulated square wave. There are various schemes, but the two most popular are PWM or pulse width modulation and sigma delta modulation. PWM is the most common technique and will be the primary focus of this section. Now, PWM, or pulse width modulation, is also known as pulse duration modulation or pulse length modulation, PDM or PLM. A pulse modulation system in which the amplitude and width of the pulses is kept in constant, while the width of each pulses is made proportional to the amplitude of the signal at the instant. It is also defined as a sample data process in which the width of each pulse is varied directly in accordance with the amplitude of the modulating signal at a particular sample point. Now, PWM encodes the amplitude values of the original audio signal in the pulse width of a square wave output, as depicted in this figure below. When the input signal is positive, the square wave output has a duty cycle greater than 50%. In this condition, the square wave spends more time at the positive rail, so when the output is low-pass filtered, the resultant average value at this point will be a positive value. Similarly, when the input is negative, it has a duty cycle less than 50%, and a zero input results in 50% duty cycle. Now, sampling, natural or uniform. The sampling method essentially involves this characteristic of the input signal, although the distinction has important implication and should be considered with the modulation scheme. The sampling refers to the amplitude representation in the modulation process. Quite simply, analog signals result in natural sampling and digital signals lead to uniform sampling. This is how we name or identify our topic. Now, identify the sampling method, the switching, and the edge. So as for my case, I have NADD. So sampling method is natural sampling, AD switching, and is it double-sided or single-sided? So as for mine, it's double-sided modulation. So all in all, it's natural sampling, AD switching, double-sided modulation, or NADD. So switching class AD. The switching method is classified into two basic groups. We have class AD and class BD, which produce two-level and three-level modulation respectively. The basic method described previously was class AD, as this two-level modulation is conceptually simpler, with the output square wave switching between positive and negative power supplies. This switching technique can also be implemented with a full bridge or H-bridge design, as shown in this figure. This extension simply operates both legs of the H-bridge complementary, which in effect always connects a path between supplies, but switches the direction of the current in the load, forming a BTL configuration or bridge tied load configuration. So the figure below shows half-bridge class AD configuration with its corresponding waveforms. So edge, single-sided or double-sided. Although the edge descriptor may seem a bit confusing, the single-sided and double-sided modulation to which it refers is very simple. Essentially, the distinction is drawn from whether the modulating carrier waveform is sawtooth or triangular, which produces single-sided and double-sided modulation respectively. So in this figure, it demonstrates a double-sided modulation results in 2 samples per sampling period. This results in twice as much information being stored for any given sampling rate. Essentially, the effective sampling frequency is doubled without increasing the actual switching rate. So here I present to you the time domain waveforms of the 4 NPWM methods. We have 2 classes, AD and BD. One is single-sided and the other is double-sided. A principal diagram of a power stage driven to achieve AD PWM. Each half-bridge voltages are denoted as V sub A and V sub B, respectively. The voltage across the load impedance is then given by this equation. Due to the inverted drive of the 2 half-bridges, the voltage across the load impedance takes 2 voltage levels, either positive or negative. The signal is sampled once in each period of the carrier signal, i.e. the sampling frequency is equal to the carrier frequency. So pulse width modulation of a sine wave has been analyzed by Black using a double Fourier series. A sine wave modulated by double-sided AD PWM can be expressed below. So we're not going to tackle them further. NADD PWM modulates both leading and trailing edges of the pulses by using a triangle shape reference. A simpler approach is the direct derivation from NADS by simple superposition. A prerequisite for the above simple addition is that the leading and trailing edge modulated waveforms do not overlap. This is obtained by a simple selection of parameters. Following by trigonometric reduction mechanisms, the series can be derived below. So this is it, the derived form. Next slide. The modulation spectrum is composed of the following components. So in components, we have the mth harmonic of carrier and IM component with their respective amplitude. The following interesting facts are concluded for NADD. The argument to the Bessel functions is have in comparison in both both single-sided modulation schemes NADS and NBDS. This is important since the ratio which the IM components are reduced is increased considerably. This is of special importance around the first harmonic of the switching frequency. Only IM components with odd are present in the spectrum, meaning that about half the HF spectrum is eliminated in comparison to NADS, i.e. a striped HES plot occurs. So similar to NADS, NADD doesn't have the pleasant spectrum at low M, since the odd harmonics of the carrier are present with maximal amplitude. From the modulation spectral characteristics, NADD must be concluded to be superior to NADS, but not as attractive as NBDS, mainly due to the characteristics at lower modulation index. The smaller skirts of NADD doesn't offset the advantages of the total elimination of carrier components that happen at lower output levels in NBDS. First off, natural sampling is much preferable to uniform sampling. While hybrid approaches offer compromised performances within this main group, so the other characteristics rank in a similar manner. So the remaining scope can be minimized to consider only natural sampling. In terms of modulation quality from best to worst, we have NBDD, NBDS, NADD, and lastly NADS. From this, one can conclude that sampling method is of the highest priority, followed by switching class, and finally by edge modulation. And with that, this ends our discussion. That's all. Thank you.